Have you ever felt like you're just adrift in this huge ocean of data? Numbers, charts, reports, algorithms.
Yeah, they all promise to unlock secrets, right?
Exactly. But actually making sense of it all can feel pretty overwhelming sometimes.
It really can.
Well, today on the Deep Dive, we're plunging headfirst into the fundamental role of statistics in data science. We want to explore that bedrock, the foundation that really grounds this powerful field.
That's right. Because while data science often conjures up these images of, complex AI and cutting-edge machine learning,
Right, the flashy
the
stuff.
flashy stuff, there's this crucial, often underestimated foundation that makes it all possible. Statistics, it's like the essential language that lets us move from just raw numbers to genuine understanding. It helps us navigate that data ocean you mentioned.
So our mission today, really, is to give you a shortcut.
Mm-hmm.
We want to turn this potentially complex information into, hopefully, crystal clear insights, showing you how statistics is absolutely indispensable for pulling knowledge out of data, for validating decisions, and maybe crucially, for helping us avoid some really common pitfalls.
Oh, definitely. Those pitfalls can completely sink in analysis.
Yeah. So we've pulled from academic papers, industry guides, even some fascinating historical notes to sort of map out this deep dive into both the practical and theoretical sides.
Sounds good. Where should we start?
Okay, let's set the stage. When we say data science, what are we actually talking about? And where does statistics fit into this whole kind of ever-evolving landscape?
Well, many sources describe data science as deeply interdisciplinary. It's about extracting knowledge from data, right? So it integrates statistics, computer science, and also domain knowledge, knowing the field you're working in.
So it's not just one thing. It's like a science, a research approach, a method, a discipline, a workflow, even a profession, all rolled into one.
Exactly. And remember that famous Harvard Business Review article? Data scientist, the sexiest job of the 21st century.
I do. Back in 2012. Seems like ages ago. But the demand for those skills, still incredibly high.
Absolutely. And at its very heart, statistics forms the fundamental core. You could call it the indispensable backbone of data science.
The backbone, I like that.
Yeah, it provides the essential tools for, collecting, organizing, analyzing, interpreting, and visualizing data, especially when we're trying to make sense of the inherent uncertainty that exists in pretty much any data set.
So without that statistical rigor, we'd just be sort of sifting through numbers aimlessly.
Pretty much like navigating without a compass, as you said earlier. You wouldn't have a clear path to meaningful conclusions.
It's interesting, too, how the name itself evolved. I read that way back in 1962, John Tukey talked about data analysis in a way that sounds a lot like modern data science.
Right, and then Peter Nair in 74 suggested data science as another name for computer science.
Well, it was C.F. Jeff Wu, wasn't it?
Yeah.
In 85, who first suggested data science as an alternative name for statistics.
Yes. He thought it would help shed some of those, let's say, inaccurate stereotypes. Like statistics just being about accounting or bean counting.
Which it definitely isn't.
Not at all. And that idea really gained momentum leading up to William S. Cleveland's 2001 paper, Data Science, an Action Plan. That really helped shape the modern idea of data science as its own field, blending different skills.
It reminds me of that quote from Josh Wills. A data scientist is a person who is better at statistics than any programmer and better at programming than any statistician.
That nails it, doesn't it? It perfectly captures that dual expertise needed. You need both.
So why should you listening care about this bedrock? Well, understanding this foundation is, I think, crucial, whether you're actively working with data yourself or maybe just consuming data-driven reports.
Which we all do, constantly.
Right, or even just trying to be well-informed in a world that's just saturated with information.
Oh.
It empowers you to sort of dissect the claims you hear every day.
And spot when someone might be leading you down the garden path, so to speak. And to do that effectively, to really dissect those claims, we need to understand the two main currents or pillars of statistical analysis in data science. Descriptive versus inferential statistics.
Okay, two pillars.
Yep. They're both crucial for getting meaningful information, but they do very different jobs. Think of them as maybe two different lenses for looking at your data.
So when we're first staring at a new pile of data, what's the first lens we use? Usually descriptive stats, right?
Usually, yes. Descriptive statistics. Its main purpose is just to summarize and describe the key features of that specific data set. You're not generalizing beyond the data you actually have.
It's purely about understanding what happened right there in your sample.
Precisely. And we all remember things like the mean, median, and mode from school, right? The measures of central tendency.
Vaguely. But In data science, knowing why you'd pick one over the other is key, isn't it? Like, why use the median for income data instead of the mean?
Exactly. Because the median isn't pulled around by a few super high earners, those outliers. It gives you a truer picture of the typical income compared to the mean in that situation. Choosing the right measure is kind of your first statistical superpower.
Okay, so that's the center. But what about how spread out the data is?
Right, that's the other half of the descriptive picture. Measures of dispersion or variability. We're talking about things like the range, variance, and importantly, standard deviation.
Standard deviation tells you, like, the average distance from the average.
Basically, yes. The average distance your data points are from the mean. It's a powerful way to quantify how much your data varies. Think about customer satisfaction scores.
Okay.
A low standard deviation means most customers feel similarly clustered around the average. A high one, opinions are all over the place.
And you mentioned IQR too, interquartile range.
Yeah, the IQR. It's less sensitive to extreme values because it focuses just on the middle 50% of your data. Good for skewed data sometimes.
And to make all this easier to grasp, we use charts, right?
Sure.
Visualizations.
Absolutely. Graphical representations are key. Histograms show you the shape of your data distribution. Is it bell-shaped? Is it skewed? Box plots give a quick visual summary of the center and spread.
And then the familiar ones like pie charts, bar charts, scatter plots.
All designed to make that data tell a story, quickly, visually.
Okay, so that's describing the data we have. What about the other pillar? Inferential statistics.
Right. Inferential statistics takes things a crucial step further. Its purpose is to make inferences, predictions, or generalizations about a larger population based on data collected from just a sample of that population.
So this is about what might happen, or maybe why something happened, looking beyond just our sample.
Exactly. We have to distinguish between the population, that's the entire group we're interested in, like all potential customers, and the sample, which is the smaller subset we actually collect data from, like the 500 customers we surveyed.
And getting that sample right is critical, I imagine.
Hugely critical. Using appropriate sampling methods is vital to avoid sampling error. If your sample doesn't accurately reflect the population, well, your inferences, your generalizations will be flawed. Garbage in, garbage out, essentially.
So descriptive stats tell us what happened in our sample. Inferential stats help us guess what will happen or what's true for the whole population based on that sample.
You got it. And it uses key methods like hypothesis testing, which we definitely need to dig into, regression analysis, for understanding relationships between variables.
Like, does advertising spend relate to sales?
Precisely. And confidence intervals, which give us a range where we think the true population value likely lies. It expresses our certainty or uncertainty about an estimate.
So the relationship is clear. Descriptive stats first, to understand the sample.
Providing that initial map of your immediate surroundings, yes.
And then inferential stats build on that to draw conclusions about the whole ocean.
That's a good way to put it. And quickly, we should also just touch on data types. Knowing if your data is, say, qualitative, like categories, yes, no, customer feedback themes.
Or quantitative numerical stuff like sales figures, temperatures.
Hey, that distinction matters because it dictates which statistical tools you can actually use. You can't calculate an average of yes and no, for example.
Makes sense. Okay, so we've laid the foundation. Now let's dive into what you call the key method, hypothesis testing. You said it's like the engine of decision-making.
It really is in many ways. It's the compass, maybe, that guides a lot of data-driven decisions. At its core, it's a formal, systematic procedure for making assumptions or claims about a population parameter.
A parameter being like the population average or something.
Exactly, a characteristic of the whole population. And you make these claims based on observations from your sample data. It provides a framework for making objective, data-backed decisions instead of just relying on gut feelings or intuition.
So it adds rigor.
Immense rigor. Think of it like a scientific courtroom trial. You start with two opposing claims.
The hypotheses.
Right. The null hypothesis and the alternative hypothesis. You gather your evidence, that's your sample data. Then you decide beforehand how much doubt you're willing to accept, that's your significance level. And based on that, you determine if the evidence is strong enough to reject the initial claim, the null hypothesis.
Okay, the terminology can be a bit tricky. Null hypothesis sounds negative. Can you break down what these terms actually mean in practice?
Sure. The null hypothesis, often written as H0, is basically the default position, the status quo assumption. It usually states there's no significant effect, no difference, no relationship.
Like, this new drug has no effect compared to the placebo.
Precisely. Or, changing the website button color has no impact on click rates. It's what you assume is true unless your evidence convinces you otherwise.
And the alternative hypothesis, H1.
That-
This new drug is better than the placebo, or the new button color does increase click rates.
Exactly. It directly contradicts the null.
Okay. And then there's the infamous p-value. This seems to trip a lot of people up. I once heard it described as surprise index.
Huh. I like that. A surprise index. It's a good way to think about it. The p-value isn't proof, but it measures how surprising your data would be if the null hypothesis were actually true.
So if the p-value is really small,
It means your observed data is very unlikely, very surprising, under the assumption that nothing interesting is happening, the null. A small p-value, usually we use a threshold like 0.05, suggests strong evidence against the null hypothesis.
you reject the null. The surprise is too big to ignore.
Right. You conclude that there probably is an effect, but, and this is critical, a small p-value doesn't tell you how big the effect is or how important it is, just that it's unlikely to be zero.
Got it. But we can make mistakes, right? Like a false alarm in your surprise index.
Absolutely. That brings us to type I and type 2 errors. A type I error is a false positive. You reject the null hypothesis when it was actually true.
So you conclude the drug works, but it really doesn't. The alarm rang falsely.
Exactly. A type 2 error is the opposite, a false negative. You fail to reject the null hypothesis when it was actually false.
You conclude the drug doesn't work, but it actually does. You missed a real effect. The alarm failed to ring.
Precisely. And related to type 2 error is statistical power. Power is the probability that your test will correctly reject a false null hypothesis.
So it's the test's ability to detect a real effect, if one exists, like how sensitive your alarm is.
Perfect analogy. Higher power means you're more likely to detect true effects. Low power means you might miss them.
And there are different kinds of these tests, depending on the data.
Oh yes, lots. Broadly, you have parametric tests, like t-tests or ANOVA. These make certain assumptions about your data, often that it follows a normal bell-shaped distribution.
And if those assumptions hold,
They tend to be more powerful. But if your data doesn't meet the assumptions, maybe it's skewed or your sample size is very small, you might use non-parametric tests.
like chi-square.
Chi-square is a common one, or Mann-Whitney U-test. These don't make such strong assumptions about the data's distribution, making them more flexible in some situations. The choice really depends on your data and your research question.
This all sounds quite technical, but where do we actually see this being used? Where does it impact you, the listener?
Oh, everywhere. Think about A/B testing in marketing. An online retailer changes the color of a Buy Now button on their website for half their visitors.
Right, version A versus version B.
Exactly. They use hypothesis testing to see if the new color B gets significantly more clicks than the old one, A. They're asking, is this difference in clicks real or just random chance?
And they often talk about confidence levels, like 95% confidence.
Yep. That relates to the significance level, usually alpha equals 0.05. A 95% confidence level means they're aiming for a 5% or lower chance of making a type I error, concluding the new button is better when it's not.
Makes sense. What about other areas?
Drug trials are a huge one. Pharmaceutical companies rigorously test new medicines against placebos or existing treatments using hypothesis testing to determine efficacy and safety. Is the new drug statistically significantly better?
Lives depend on that.
Absolutely. Also in public policy, governments use it to evaluate if new programs, say an educational initiative or a job training scheme, actually have a measurable impact.
Even in really advanced tech.
For sure. Think autonomous vehicles. Engineers use hypothesis testing to compare different algorithms for detecting pedestrians or other cars. Is Model X significantly more accurate or faster than Model Y? Safety relies on getting that right.
So it really does underpin critical decisions across almost every field.
It absolutely does.
Okay, moving on. Let's talk about statistical modeling and how it relates to the buzzwordy field of machine learning. What exactly is statistical modeling?
Well, you can think of statistical modeling as a more, perhaps, formal way of using statistics to understand relationships and make predictions. It's about building mathematical representations of how data is generated.
So creating a sort of mathematical description of reality based on data.
That's a good way to put it. It often involves making explicit assumptions about the data and the relationships between variables, random and non-random variables. The goal is often to understand why things are related.
To understand correlations, analyze information strategically, and generate predictions or visualizations.
Exactly. And there are many techniques. Linear regression is a classic trying to predict a continuous value, like house price, based on features like size and location.
Simple and multiple regression.
Right. Then there's classification predicting categories. Logistic regression is common here, predicting things like customer churn, yes, no. You also have tree-based methods like decision trees, random forests, boosting.
Those sound more like machine learning.
They bridge the gap. And you also have unsupervised learning techniques like k-means clustering, which finds groups in data without you telling it what the groups are beforehand. That's often considered both statistical modeling and ML.
Okay, so that leads to the big question. How does statistical modeling really differ from machine learning? People seem to use the terms almost interchangeably sometimes.
Yeah, it's a common point of confusion, and honestly, the lines can be blurry. But a key distinction often lies in the primary goal.
Which is?
Machine learning often prioritizes predictive accuracy. The main goal is to build a model that makes the best possible predictions on new, unseen data, even if the inner workings of the model are complex and hard to interpret.
Learning from data to predict without being explicitly programmed for every rule.
Exactly. Statistical modeling, traditionally at least, puts more emphasis on inference and explanation. The goal is often to understand the relationship between variables, to quantify the effect of one variable on another, and to test hypotheses about these relationships. Interpretability is usually key.
So it's kind of like statistical modeling. Explain why machine learning predict what. Is that too simple?
It's a useful simplification, though not always perfectly true. Statistical models aim for interpretability. You can look at the model coefficients in a regression, for instance, and understand the estimated effect of each variable.
You can tell the story of the data.
Right, right. ML models, especially complex ones like deep neural networks, can sometimes be black boxes. They might give incredibly accurate predictions, but understanding how they arrived at that prediction can be very difficult.
So interpretability versus accuracy is a trade-off sometimes.
Yeah, often, yes.
Yeah.
Though there's a lot of work in explainable AI trying to bridge that gap. But it's crucial to remember they're not mutually exclusive worlds.
They're intertwined.
Deeply intertwined. Many ML algorithms are built directly on statistical foundations. Think about linear regression or logistic regression. They are fundamental statistical models and are used as basic machine learning algorithms. Statistics provides the theoretical underpinnings for much of ML.
So they're really two sides of the same coin, both essential for navigating that data ocean.
Absolutely. You need both perspectives, both toolkits.
Okay. So we have these powerful tools, statistics, modeling, ML, but even with all that, things can go wrong. Let's navigate what you earlier called the minefield of common pitfalls in research and analysis.
Yes, this is so important. Martin van Smeeden, a medical statistician, has written compellingly about this. He warns that even with a strong statistical foundation, easily avoidable errors and inaccuracies can basically ruin a study and make the research much less useful or even misleading.
That's a serious warning. It sounds like you can have the best intentions, the best data, the best models, but still fall into traps.
Absolutely, and it starts right at the very beginning with having unclear research questions and aims.
How so?
Well, if you aren't crystal clear on whether your main goal is to predict something or to explain why something happens or just to describe a situation, you're already setting yourself up for trouble. They require different approaches.
Especially the explain part, right? Mistaking correlation for causation.
That's a huge one. It's so tempting to see two things happening together and assume one causes the other. If your aim is explanation, especially with observational data where you didn't run an experiment, you have to be incredibly careful. Thinking about causal inference methods becomes really important.
Okay, what's another major pitfall?
Insufficient data. Having a sample size that's just too small for what you're trying to do.
Like your bucket of water in the ocean analogy earlier.
Exactly. This can lead to overfitting. Your model learns the random noise and quirks in your small sample too well, and it thinks those quirks are real patterns that apply to everyone. It won't generalize well to new data.
And it also means you lack precision and power.
Right. Your estimates will have wide margins of error, and you might completely miss real effects simply because your sample wasn't large enough to detect them. And beware of those simple rules of thumb. For sample size, they often don't apply well.
Okay, sample size is key. What about how we prepare or handle the data?
Big issues there, too. Have you heard of p-hacking? or sometimes called data dredging.
Is that where you just keep analyzing the data in different ways until you find something statistically significant?
Precisely. You run dozens, maybe hundreds of tests, looking for anything with a p-value below 0.05, and then you selectively report only those significant findings, maybe even building a story around them after the fact.
That sounds dishonest.
It can be, or sometimes it's done unintentionally, but the result is the same. A very high risk of false positive findings. You're basically highlighting random chance as if it's a real discovery. It's like throwing spaghetti at the wall and only talking about the one piece that stuck.
Yikes. Okay, what else in data prep?
Another one is what Van Smeeden calls dichotomania. It's this sort of natural tendency people have to take continuous measurements like age or blood pressure and chop them up into categories young versus old, high BP versus normal BP.
Why is that bad? Seems simpler sometimes.
It seems simpler, but it's usually a bad idea because you throw away so much valuable information, you lose all the nuance. Someone who is 59 is suddenly in the same old bucket as someone who is 89. It reduces the power of your analysis and can hide real relationships.
Right. Losing the detail. What about data quality itself?
Major source of pitfalls. For instance, how you handle missing data. Just ignoring it or deleting rows with any missing values is often the default.
But that's bad.
It can be really bad. Ignoring missing data often makes strong, hidden assumptions about why the data is missing, which can seriously bias your results. Proper methods, like multiple imputation, are more complex, but usually much better.
And what if data is, like, grouped?
Clustered data. That's when your data isn't fully independent. Maybe you have measurements from patients within different hospitals or repeated measurements over time on the same person.
So some data points are more alike than others.
Exactly. If you don't account for that clustering in your analysis, you might artificially inflate your certainty and find significant results that aren't really there. You need specific methods to handle clustered data.
This all seems to lead towards misinterpreting the results, especially statistical significance.
That's a massive one. We hear statistically significant all the time, and it sounds so definitive. But remember, a statistically significant result doesn't automatically mean the effect is large or practically important.
It just means it's unlikely to be due to random chance alone.
Exactly. You could have a tiny, trivial effect that's statistically significant if your sample size is huge. And conversely, a non-significant result doesn't prove there's no effect.
The absence of evidence is not evidence of absence thing.
Right. Maybe the effect is real but small, or maybe your study just didn't have enough power to detect it. And interestingly, just blindly removing non-significant variables from a model, that can actually increase overfitting sometimes.
Wow. Okay. And you also mentioned ignoring uncertainty.
Yes, the tendency to just focus on the single point, estimate the average effect, say, and ignore the confidence interval around it. That interval tells you the range of plausible values. Ignoring it means ignoring the uncertainty in your finding. Some researchers are even calling to abandon the whole concept of statistical significance because it's so often misused.
That's a radical step.
It is, but it highlights how problematic the misinterpretations can be.
Finally, you mentioned the challenge of making causal claims earlier.
Yes, this is perhaps the trickiest pitfall, especially with non-experimental observational data. Distinguishing true causes from mere correlations is incredibly hard.
You mentioned confounding before, like the ice cream sales and shark attacks example, where summer heat was the confounder.
Exactly. A confounder is a third variable that affects both your variable of interest and your outcome, creating a spurious association between them. Failing to account for confounders is a major source of error.
Are there other similar issues?
Yes. There's also something called collider bias, which is more subtle. That's when you adjust for a variable that is caused by both your exposure and your outcome. Adjusting for a collider can actually introduce bias where none existed before. It's complex stuff.
It sounds like just saying association instead of cause isn't always enough.
Often, it's not really a solution. It avoids the word cause, but the implication is often still there, and the potential for misinterpretation remains. And Van Smeeden also warns against the table 2 fallacy, where people look at a regression table adjusting for confounders and then wrongly interpret the coefficients for those confounders as if they represent causal effects.
So many ways to go wrong. Is there any pitfall that's easy to avoid?
Yes, thankfully. Van Smeeden says the easiest one to avoid is incomplete reporting. Just be transparent. Use established reporting guidelines for your field, like Consort for trials, Strobe for observational studies. They provide checklists to ensure you report all the essential information so others can properly assess your work.
Transparency is key. Which leads us naturally to the final, crucial topic, the ethical compass in data science.
Absolutely critical, because all these pitfalls we've discussed, they don't just lead to bad science. They can have real-world ethical consequences, especially since data science often deals with personal, sensitive information.
The power of data comes with responsibility.
Immense responsibility. It's not just about what you can do with data, but what you should do.
So what are some of the key ethical concerns we need to keep in mind?
Well, privacy violations are a big one. The risk of data breaches if sensitive information isn't handled with extreme care. Techniques like anonymization and de-identification are important, but not always foolproof.
And what about bias? We hear a lot about algorithmic bias.
Yes, bias perpetuation and discrimination is a huge concern. If models are trained on historical data that reflects existing societal biases, say, biased hiring practices in the past, the model can learn and even amplify those biases.
Leading to unfair outcomes in things like job applications, loan approvals, even criminal justice.
Exactly. It can perpetuate cycles of discrimination, often unintentionally. Identifying and actively working to mitigate bias in data and models is an ongoing ethical necessity. It's like constantly checking your ship's course for drift.
Are there broader societal impacts too?
Definitely. Issues like algorithmic transparency or the lack thereof. Can we understand how important decisions affecting people's lives are being made by algorithms? Accountability is another, who is responsible when an algorithm makes a harmful error. And of course, the potential for misuse of data for manipulation or surveillance.
And this ties back to the pitfalls, right? Misinterpretation, making unjustified claims.
Absolutely. If you overstate your findings, ignore uncertainty, make causal claims without strong evidence, or fail to report limitations, those statistical failings can lead to really poorly informed decisions by policymakers, businesses, or individuals with serious ethical consequences.
So ethical data science isn't just a separate checklist. It's woven into the entire process.
It has to be. It demands critical evaluation at every step of the data, the methods, the models, and crucially, the potential impact on people and society. It requires humility about what the data can truly tell us.
Okay, so we've taken quite a journey today, haven't we? Through the foundations of data science, the core role of statistics, the key methods like hypothesis testing, modeling, and critically, the pitfalls and ethical duties.
It's clear, I hope, that statistics isn't just, crunching numbers in the background. It's the fundamental framework. It provides the rigor, the structure, the language for doing insightful, reliable, and ethical data science.
It really underpins everything, doesn't it? From figuring out if a marketing campaign worked, to validating whether a new drug is safe and effective, to evaluating public policy. It's that deep current guiding our whole deep dive into data.
And understanding these concepts, even at a high level, empowers you, the listener. It helps you to critically assess the flood of data-driven claims you encounter every single day. In the news, at work, everywhere.
It helps turn that feeling of information overload into a feeling of informed understanding. Give you that compass in the data ocean.
Exactly. It helps you ask the right questions.
So, as we wrap up, here's maybe a final thought for you to mull over as you navigate your own data journeys. Given how complex data is becoming, and with the incredible rise of AI, how might these traditional statistical concepts we've talked about today need to evolve? How will they adapt to meet these new challenges?
That's a huge question for the field.
It is. And perhaps just as importantly, what role do you play in your own context in advocating for the responsible, ethical, and genuinely insightful application of these powerful tools?